Um, Super excited to introduce Leo Singer. He's a civil servant at Goddard, works on LIGO, works on ZTF, works on also one of the lead developers on GCN, so does a lot of the software development. So this afternoon session is a small change of pace. So we've been doing, as the summer schools described, machine learning last 2 days, the next 2 days. But there's a slightly different but related topic called mixed integer programming, which is a technique we can use to optimize sort of constraint-based problems that might be kind of an interesting technique to use for some of the problems that we've been facing so far. We've been addressing in summer school, and so Leo's an expert. We're really excited to hear from him. So
I don't know if I'm an expert. I'm something I've used. So actually, mixed integer programming is a modeling and optimization approach that has been around for decades. And what happens is techniques that are useful for optimization and planning and solving large complex problems start out as being considered an AI topic, and eventually they become machine learning topics, and then eventually they just become algorithms. And so mixed integer programming has been around for so long that it's just kind of an algorithm. I don't know how much you've talked about LIGO and multi-messenger astronomy yet. Have you talked about multi-messenger astronomy? Okay, so you know that we have gravitational waves and electromagnetism, and we get all kinds of amazing science when we are able to do both kinds of observations of the same objects. And is it useful if I explain what that allows us to do? Yeah, okay. So if we have gravitational wave observations of a neutron star merger, then that allows us to estimate the luminosity distance to the source, because gravitational wave sources are standard sirens. So they produce a known luminosity for a given set of masses, and we observe a given intensity of gravitational waves. And so knowing the intensity and the luminosity, we get the distance. We get the progenitor masses, the masses of the two compact objects that merged, although that mass is also tied up with the redshift, which we don't know just from gravitational waves. We also can get the spins. We can determine something about the equation of state of matter from the late phase of the gravitational wave signal. If there was a neutron star involved, we can do tests of general relativity. On the electromagnetic side, if we find a counterpart, we can try to identify which galaxy is the host of that counterpart, and then we get the redshift of the galaxy. And then by combining that redshift with the luminosity distance, we can measure the Hubble constant. With multi-wavelength observations of the afterglow of the gamma ray burst, we can tell something about the jet profile. So when the merger produces a gamma ray burst, the gamma ray burst shocks the medium around the merger, and the opening angle of that jet is something that we can measure from the light curve, but combining that with gravitational waves, we also get the inclination angle of the binary. We get the velocity of the ejecta from the explosion, its temperature, and its composition. And when we combine that with mass estimates from gravitational waves, we can sort of tease out what is what kind of remnant compact object is formed as a function of what masses go in. And we can do all kinds of other cool things. So gravitational waves and electromagnetic observations tell us different kinds of things about about a bunch of different parameters. So with gravitational waves, we determine the sky position, but we determine it pretty poorly. Once we combine the gravitation, once we combine the luminosity distance with the sky position from the, finding a counterpart, that gives us that breaks a degeneracy between luminosity distance and inclination angle. So we start out having, about 30% uncertainty in the luminosity distance of the source. And if we know the redshift, then that uncertainty goes away. Knowing the luminosity distance, the inclination angle, and knowing how bright the gamma ray burst was, we can tell exactly how luminous gamma ray bursts are without having to guess about the opening angle of their jets. That gives us the true rate of mergers that launch relativistic jets. So as I said, we get progenitor masses from the gravitational wave observations, although there's also a degeneracy with redshift. So if we measure the redshift independently by taking a spectrum of the host galaxy, then we know the progenitor masses in the rest frame very accurately. And then, as I said, combining the redshift and the luminosity distance, we get the Hubble constant. So we have a global network of gravitational wave detectors, LIGO Hanford, LIGO Livingston, and Virgo. CAGRA, actually, this is outdated. CAGRA is just, actually, I don't know if it's online right now, probably not, but it is no longer it's kind of continuously being commissioned, but it's actually done observations. And LIGO India is under construction. So having this network of gravitational waves allows us to triangulate the positions of the sources of these signals, which in turn allows us to point telescopes and try to find counterparts. But there's an obstacle, a very serious obstacle to finding the positions of these counterparts, that there is a very, very large mismatch between the resolution that we get with typical optical telescopes versus the localization uncertainty. And so fortunately, around the same time that advanced LIGO was just reaching some appreciable sensitivity, we were well along in this sort of revolution in time domain astronomy, which is the whole reason that we have workshops like this. So thanks to experiments like ZTF and Dark Energy Survey and PanSTARRS and LSST, we have we have larger and larger CCDs on robotic telescopes, large fields of view, and combining that with automated analysis and machine learning, we can take images of the whole sky and go back. This is the whole raison d'etre of ZTF. But because we have these very large fields of view and these survey telescopes, we can repurpose them to do targets of opportunity, where we use that telescope to tile a region of interest that covers the localization region of the gravitational wave event. So how do we decide where to point our telescope and in what order to observe these fields? So this is an optimization problem, and we want to maximize the probability of detecting the counterpart of the gravitational wave source. Now, in this lecture, I'm going to talk about some algorithms and some approaches for solving a simpler subproblem, which is maximizing the total integrated probability within the localization that is contained within the union of the footprints of all of the fields that we observe. So these sort of orangish, reddish color maps, these are maps of posterior probability density across the sky. So they're deeper and redder where it is more likely that the signal came from, and lighter where it's less likely. So we want to take all of the ZTF tiles that we've picked out, and we want to ask if we integrate this probability density function over the union of all of these shapes, what is the total contained probability? And we want to maximize that by intelligently picking which fields to observe. So it's a constrained optimization problem. We can only observe when it's night. Go ahead, Ethan.
The last slide. Can you explain the difference between these two objectives, a simplified version?
Well, so if we want to maximize the probability of detecting the counterpart, we also have to pick, we have to decide how long does each exposure have to be to reach the right SNR? We have to consider that we know something about what the light curve looks like. And so if we want to detect it, we want to schedule the observations when we think that the signal is going to be bright. If we schedule the observations too late, then the source will have faded
So the
away.
simplified one is just considering the gravitational wave.
That's right, yeah. So this is, as I said, this is a constrained optimization problem. So some of the constraints are that it must be nighttime. We have to observe when the source is at sufficiently low air mass. So air mass is a measure of how attenuated the light from a star is as a result of how much of the Earth's atmosphere it is passing through. And air mass is a dimensionless quantity that describes that amount of attenuation, and it's related to the angle from the zenith. So it basically what it's saying is that we want to observe sources when they're high in the sky. We have a cadence constraint, which is that we want to visit each field that we select multiple times because we rely on detecting the same source once and then again a second time to rule out asteroids that are moving across the image that we wouldn't detect twice in a revisit. So we have some constraint on the minimum time between exposures. The exposures can't overlap with each other unless we have a quantum mechanical telescope. You can't observe the same field, two fields at the same time. And there's a time limit. We want to complete the observations within a single night. So actually, the cadence constraint we're not going to deal with in this talk because that is we're just going to plan a single epoch of observations. So just picking which fields to observe is a problem of literally astronomical size. So ZTF has a grid of pointings that has about 1,000 potential places that we can look. A reasonable exposure time for follow-up with ZTF for gravitational wave events is a few hundred seconds. We can do about 100 such visits in one night. You do the math and you come up with this number of possible choices of which fields to observe. And this is not even, taking into account. This does take into account order in which to observe them. So there are a bunch of approaches out there that people have developed that actually solve this kind of problem in a pretty routine manner. So Spike is the scheduler that was developed for the Hubble Space Telescope, and it uses an approach called constraint satisfaction or constraint programming, which is actually closely related to the technique that I'm going to teach you in this talk. The Swift Observatory, Neil Gehrels Swift Observatory, is a gamma ray, X-ray, and optical UV robotic telescope that automatically detects and follows up gamma ray bursts and observes hundreds of sources a day. And it can do tiled observations for gravitational wave events. And it's this, the algorithm that it uses is a dynamic fuzzy constraint satisfaction solver, which I don't really know how that works, but it looks cool. Las Cumbres Observatory is a network of small robotic optical telescopes all around the world. It's really neat. The telescopes are in a way almost like mass produced. They have a few models of telescope that they just built, many copies of and deployed them at sites around the world. And so they have this scheduler where science users can submit targets that automatically get added to the queue and get slotted in wherever they can. So this is sort of a multi-user, multi-telescope network. And this uses the technique called integer linear programming, which is exactly what we're going to be talking about. And the ZTF scheduler also uses integer linear programming. The Vera Rubin Observatory does not use integer linear programming. It uses this framework called Markov decision processes. Excuse me. And then lastly, I think lastly, yeah, there's WEMOpt, which is a multi-facility scheduling toolkit developed by Michael Coughlin and many others, and is mainly designed for scheduling these multi-messenger targets of opportunity. And it has a large catalog or a large selection of different heuristic algorithms or different rules of thumb that do a really good job in practice for a variety of different telescopes, including ZTF. And this is the scheduler that we actually use for gravitational wave follow-up right now. So there are, broadly speaking, these at least these 5 different solution strategies for scheduling problems. There's exhaustive search, where you enumerate and check each possible solution. So it has the advantage that it's trivial to implement. It has the disadvantage that we can't complete an exhaustive search even for ZTF within a Hubble time. We have greedy search, which takes a locally optimal move at each step in the iterative process. So the way this would work is you pick the ZTF field that contains the highest probability, and then you cut that field out of the sky map, and then you take the next field that contains the highest probability and cut that out of the sky map, and so on and so forth. And so this has the advantage of being easy to implement and very fast. It is generally not going to be globally optimal. You have heuristics, which are specialized and purpose-built rules of thumb. So these are sort of strategies that we design. And they have the advantage of having very predictable behavior because they do exactly what we tell them to do. It has the downside that we, instead of thinking about, okay, what is the behavior, what is the thing that we're trying to optimize, and what are the constraints? Instead, we have to focus on how we meet those objectives and constraints. Genetic algorithms, you start with a possible solution and you make random changes to it. And when a change results in a better objective value, you keep that solution. And when it doesn't, you throw it away. And this is, straightforward. It can be combined with any of these other strategies. It has the disadvantage of being unpredictable and sometimes slow. And then lastly, we have mixed integer programming, which is where you take an optimization problem that includes variables that represent decisions that you have to make between different alternatives. And you express that problem as a linear program, which I'll explain a little bit more what that is, with both real and integer variables. And it has the advantage of being very expressive. There are automated solution methods and automated solvers out there. You can, any set of, you can basically write your optimization problem as pseudocode and then convert that pseudocode into equations and inequalities and then turn the crank on a solver. It does have plenty of downsides. This is an NP complete problem. Some problem formulations are going to be more computationally tractable than others. But it's been around for quite a while, and it's a well-established methodology. So I just have two little pretty videos to show what you can do with mixed integer programming before I explain what it is. So this is an observing plan for a LIGO event that, based on the date, probably was in 2003, and it took about a minute and a half on my old laptop that I had before this one to solve it. And so you can see it's, in this case, I've actually set it up so that it has to visit Eastfield at least twice. And then this is another mixed integer programming scheduler that I wrote for a couple space missions that I've worked on. One is, so both of these space missions are ultraviolet transient telescopes. Dorado was a concept study that did not get selected, and UVEX is a much larger UV space telescope that was selected and is going to fly in the mid-2030s, I think.
I think that's the claim to this thing, early 2030.
Early 2030s? Yeah. Go ahead. Oh, target of opportunity. Okay, so I mentioned that I haven't explained what mixed integer programming is, or mixed integer linear programming is yet, but I will. So unfortunately, although this is a well-studied method, the software for using this method is pretty expensive because there are serious commercial applications, and so just like you don't have many options for free and open source CAD software or design software, and this is just like that. They're mixed integer programming solvers. The state of the art is these three commercial products: Express, which is actually a product of FICO, which is the credit reporting agency; Cplex, which is a product of IBM; and Garobi, which is it's a product of Garobi is both the product and the name of the company. But so these are really expensive if you're in industry or if you are a government employee like me. Fortunately, there are free licenses for anyone who is a student or faculty at a university. There are several really good open source solvers, and I've listed 4 of them here. And they have very similar interfaces to Garobi and Cplex and FICO Express, but they're just not nearly as fast, and they will not be able to solve as many problems as Garobi and Cplex and Express can. We're going to use Pies for the rest of this talk because this is a solver that has really nice first-party Python interface, and also has an interface that's been built into SciPy since 2022. Okay, so let's dig into it. So linear programming is a topic that you might have spent about 3 minutes on in a high school algebra course, and you may have done a single problem with it at most, and then forgotten about it. Which is a shame because it's a really useful technique. So linear programming is where you want to maximize a linear combination of decision variables subject to constraints that are linear inequalities. It was studied as early as the 19th century by Fourier, but the big breakthroughs happened in the 1946 to 47 because there were operations research optimization problems that were important for the war effort. So there are algorithms that can solve any linear programming problem if a solution exists in polynomials. So there are important applications in economics. We've used a linear program to balance a stock portfolio, applications in game theory, industrial engineering, so on and so forth. But this is not something that you have to shell out a lot of cash for because it has polynomial time algorithms. It's pretty straightforward. So we're going to stop here for exercises 1 through 3. And so hop over to the notebook exercises.ipynb. Now, if you are on a Windows machine, you will definitely want to use Colab rather than using the notebook locally, because there are some dependencies that don't work on Windows. I guess raise your hand once you have the notebook open either on your computer or in Colab.
There's no GPUs mixed in feature of the notebook.
No.
Okay.
Like the draw variables, that is not related to this. Not like
So Lagrange multipliers are, that is, that's useful when you, that's a way to transform a constrained optimization problem into transform a system of equations and inequalities into a system of equations. And usually when you use Lagrange multipliers, you're optimizing something that you have the constraints bound from above. Whereas with linear programming, you have constraints that enclose the feasible region on all sides. And the thing that makes that complicated is that you have to check for possible solutions at all of the intersections of all of the constraints. And so there is something like Lagrange multipliers that is part of it, and those are called slack variables. We'll not have to worry about that because that's something internal to these solvers. So the magic of linear programming is a specific algorithm for how to efficiently search all of the solution candidates.
I have a question.
Yeah.
And so I've just heard this term being thrown around. Do you know if it's related to dynamic programming?
Yes. Yeah.
So
Yeah.
is this a subset of dynamic?
Well, so yeah, that was on the slide, I think, but right. So what this little cartoon here shows is that so that line represents a cross section of an objective function. So you have to imagine this as a two-dimensional slice. There's some n-dimensional space. And that objective function is a hyperplane. And this system of inequalities is represented by that shaded polygon. So you can show that if an optimum exists, that it must be at one of the points where the planes that form these that describe the constraints meet, and the breakthroughs that occurred in the 40s and 50s were the invention of dynamic programming, which is a general approach to constructing algorithms where you decompose the solution into partial solutions, and you keep track of those partial solutions and you reuse them as you go. And so there is a dynamic programming algorithm to traverse the edges of this polytope that encloses the feasible region in the quickest possible manner. Yeah, go ahead.
So the solution is always on like the constraint boundary. Is that
Correct. Yeah. Yeah. Okay. Raise your hand if you have the notebook open. See a couple hands still down. Raise your hand. Put your hands. Raise your hand if you have the notebook open or do not care about having. Does anyone have? Okay, put your hands down. Raise your hand if you need help with the notebook. Okay. So, right. So run this. Go ahead and run this first cell. This is just going to install the dependencies that we need, which are LIGO.SkyMap, a particular version of SciPy and NumPy, and HiSPy, which are the first-party bindings for this solver. Raise your hand once your dependencies are installed. Raise your hand if you fear that they are not working. So, right. So this is just our the sort of canonical form of a mixed of a linear program. So here's our sort of first sample problem. This is not an astronomy problem, or at least not an observational astronomy problem. So, all right. Who wants to read this? Go ahead.
The summer school. There are 30 students, each will write 20 lines of code with a couple of each, 100 with a couple of coffee, 100 with muffin, 20 for donuts, because don't do updates. That's it for this. Here are the unit prices for the E1, coffee 11, muffin 2, donut 650, and bagel $2. Each student must have at least one drink and at least one pastry. What defines pastry?
A muffin, donut, or bagel. Yeah.
At least one of which must be a donut. Okay, the Muffin Man Lemonade Lab has a budget of 180 per snack. How many of each snack should they buy? How many lines of code should we try?
Okay, so first we're going to write down a linear cost function and a system of inequalities to model it. Yeah, go ahead.
I have a question.
Yeah.
What are you trying to maximize here? Are you trying to maximize the lines of code written?
Yes.
Oh, okay.
Yeah. That is the only measure of a student's productivity.
At least one of which must be a donor. That means I need to portray at least one student as a donor.
No.
All the categories that each student eats, that has to be at least a donor, or
So if
I
there are
have to buy a donor and the other 19 can be something more tasty.
no, every single student must have a donut. They can have more than one pastry, but they must at least have a donut. So actually, yeah, you're right. So have the at least one donut already automatically satisfies the at least one pastry constraint. So All right, who wants to try this? Who wants to write down the cost function? So remember the, so let's actually, put this canonical form up here. So we remember what we're trying to write down. So actually, oh yeah, so this is an important note. So the usual definition of this canonical form is, find the vector x that maximizes C transpose x. But because SciPy uses the convention that it's minimization, that's how we're going to define this canonical form. We're going to minimize C transpose x subject to AX is less than or equal to B, and X is greater than or equal to 0. So we need to write down C, which are the coefficients for the objective function of the cost function. A, which is the matrix of coefficients for the constraints. B, which is the vector of constants for the constraints. So who wants to write down C? Let me just hand this marker to some poor unsuspecting soul. No one raises their hand. So oh God. Okay, come on up, Ethan.
You see the lines of code per food item.
Well, that's the question. So what? So the objective is to maximize the total number of lines of code written.
So then C is the lines of code per food item, and then X is the number of food items that you should be among students, right?
Exactly. Yeah.
So should I write down verbally or?
Just write it down. Write down C.
Oh, okay.
Because everyone's going to need this for their code.
Question.
Yeah.
We're trying to minimize those. Should it be the cost per line instead of the number of lines per cost?
Cost per line instead of the lines per cost. So you're thinking like the reciprocal?
Right, like it takes $1 for 20 lines of code per T, right?
So you're on
Trying to minimize.
That's close. Any other tweaks that anyone wants to make to this cost function?
But there should be a minus.
Should be minus sign. Go ahead and add a minus sign.
This is because we're minimizing.
Yeah. Yeah.
Maximizing lines of code.
Maximize the lines of code, but cannot remember that the exercise here is to write it in the canonical form so that we can pass it to SciPy in our code exercise in a moment. And SciPy wants to minimize. That's why we have to negate it. Yeah. Okay, who wants to come up and write down A? You already answered.
I just read the question.
Oh, okay. Go ahead.
So A with a straight, right? So that means that. Okay. A is, it tells us how much stuff they all have to eat, right?
Oh, actually, you know what? I realized I jumped ahead to exercise 2. So as I've written in exercise 1 is write down the cost function in the system of inequalities, model the problem. Exercise 2 is write down the coefficients. So it might help to write down the system of inequalities first.
What do you mean by system of inequality?
So like x1 plus x2 is less than or equal to whatever.
X1 is less than or equal to.
And actually, let's use zero-based indexing because this is Python.
I'm still not sure what you mean by the Why this is maybe what it is, I'm missing something.
Well, let me write down one inequality to get us started. So the vector X is the number of each type of treat in the order tea, coffee, muffin, donut, bagel. So we have the constraint that each person must have at least one drink. There are 30 people. So we have the constraint x0 plus x1 is greater than or equal to 30. Yeah.
Or this is the AX plus.
Yeah. Yeah.
All right,
So so we have,
that's,
and then, so let's do at least one pastry now.
X2 plus X3 plus X4, right? This is 30 and 30. Or, and then at least one of which must be a donut. Means X3, 0, 2, 1. No, 3. Donuts are 3. So X3 is greater or equal to 30.
Yeah.
Okay. And I have to put this in A.
I think there's one more constraint.
Oh,
You know what the last constraint is? Yeah.
It's the total budget.
Yeah.
all right. So then X0 times should be total prices.
Sure. Yeah. Definitely.
Okay, so X0 times 1 plus X1 times 2 plus X2 times 2 plus X3 times 3 plus X4 times 2 has to be smaller or equal than 180.
All right. Thank you. Maybe see it. All right. Okay. Now, who wants to write down A and B? So take these. Yeah, come on up.
Nice big fun matrix. So we're gonna have 1, 1, 0, 5, 0. So that's this side here. Then this one is 0, 0, 1, 1, 1. It's here, and then this is 0, 0, 0, 0. And then this is going to be the costs. So it's going to be 1, 2, 2, 3.5, 2. So that's this matrix. Then X is like this. This is going to be
Less than or equal to.
well, this is an issue because these are greater than, so something needs to be negative somewhere. So let me just write this down and I'll fix the negative signs in a second. So this is going to be all the constraints here, so 30, 30, 30, 180. So this one has the right sign, but these need to all be flipped. So if I remember high school math, I think if I just give all these negatives, that flips it.
Yeah.
The what? Yeah, both sides.
Yeah.
So minus, 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 minus.
Nice. I like it. Does everyone agree? All right.
I have a question.
Yeah, go ahead.
I don't understand how this term is that student that at least one, drink. I mean, we know that the students will have 30 drinks and we have 30 students. But what prevents the students to take 30 drinks and the other students to take 0?
Well, indeed, so we're not, so the Muffin Man Poopy Pants, excuse me, that's a. Rick and Morty. Muffin Man Lemonade. Oh my gosh. Does not concern itself with fair allocation of snacks to students. They are only concerned with buying the appropriate number of snacks. The fair allocation is left to the students. Honor systems. Yeah. That's okay. Good question.
All right, so now we are going to use scipy.optimize.linprog
To solve this problem. So I have set this up for you. You have your matrices, your matrix elements. Plug them in and see what you get.
Well, it's probably okay if you just input them as lists, but because I bet that optimize.linprog will convert them for you automatically, but yeah, I would do numpy.asArray. And then I can't see that far. Oops. Yep.
The, yeah, so in general, the greater equal sign could also be meant with respect to some metric, right?
No, because this is linear programming. This is only this solver only works with linear systems. So if you can. So this is not a nonlinear programming technique. If you want to solve a nonlinear optimization problem, then you would need to linearize it. For box data.
I mean, the matrix multiplication of matrix operations would still be linear, but I could do the optimization with respect to, say, the square, like the Euclidean norm.
I guess so. I don't know. I haven't thought of that. I don't know. That's more math than I know.
Okay, raise your hand once you've gotten some output. Poking the stick. I'm poking the sticks.
Yes, you.
I got
Oh, you're saying you're not. Okay. Okay, raise your hand if something is not working. Okay, is everyone all right if I move along? Someone, yeah, go ahead.
I got a different answer.
Really? What answer did you get?
Oh, I need to put some minus signs.
I want to make sure we're all on the same page for this because we're going to use this solution in subsequent steps.
Is everyone okay now? Do I move on? Someone say yes, and I will. Yeah, go ahead.
I would assume that, as we just discussed the tea, but the coffee is 2.5 times more cost efficient than the tea.
Yes.
So if I manage to increase my code output per tea
Yeah.
above 40 lines, my tea should become the preferred option.
Yes. So let's see what happens if we do that. If we make tea just as good, just as effective at lines of code as coffee, we buy teas instead.
I just toyed around.
Yeah.
Slightly above 40, I still get stuck on the coffees, although I would assume things change to
What
40,
what value did you put in for the?
40.0001. That still tells me the coffee is not a trick, but it feels counterintuitive to me.
Maybe it's like, maybe it's being used for one.
Yeah, I don't know. It'd be interesting to figure out where that where it changes.
I also have a question. So like,
Go ahead.
yeah. So when we are defining the objective function, uh, you go to the question. So I think it's better if we are on the question. Yeah. So when we are defining the cost function, shouldn't we add like all the variables and then uh, so like you would have the cost of bagels, tea, coffee, muffin, donut, and bagel, uh, multiplied with their respective prices, which should be greater than, which should be less than or equal to 180, right? So why have we kept minus 20, minus 100, minus 100, minus 20, minus 70 in the cost function?
Because scipy.optimize.linprog only does minimization. So
Okay. Yeah, maybe uh, we can have bounds on the variables and then do the same thing. Probably will help. I'm just guessing.
well, so the canonical form which SciPy has us input the problem in has the bound that x is greater than or equal to 0. So we didn't make any changes to that. And also, it's not really necessary to bound the variables in this problem because there is already the costs or the number of each type of snack is bounded from above.
Yes.
And if we allowed any of the variables to go negative, it would only hurt the cost function.
Yes, I understand.
Yeah.
Yeah. Yeah. Thank you. Thank you so much.
You're welcome. Any other question there online? Okay, I'm gonna move on. Okay, so yeah, go ahead. Yes. Yes, that's the next problem. When we went to Dunkin' Donuts, we ordered we ordered 38 cups of coffee, and we cut one in half. All the coffee's spilled out. So clearly we need to restrict all of these variables to be integers. So integer linear programming is just like linear programming, except all of the variables are integers. Mixed integer linear programming is just linear programming where certain variables have to be integers and others can be reals. And actually, I'm going to switch back to my slides very briefly. So this is now a much more computationally challenging problem. It's non-convex and it is NP complete, which means that there is no, well, it means that there is not a polynomial time solution to it. However, there are a collection of algorithms which go under the term, or there are a collection of strategies which go under the heading of dynamic programming that we can use to search all these possible solutions in a relatively efficient way. So these algorithms are well studied because this type of problem is very useful in industrial process optimization. It's one of the algorithms that you could choose to write software to automatically route printed circuit board traces. It's used in oil and gas exploration and so on. So that is why those three commercial solvers are so expensive, because there really is money to be made here. But these powerful general purpose solvers have been growing since the 80s, and so we're gonna use it. So exercise 4 is just, we're going to, yes, go ahead.
Solvers. Is the benefit there algorithmic or on the like compute optimization side?
So the commercial so there are, so if you let the so if you terminate, so you can either let the solver run until it finds a global optimum, if one exists, or you can give it some time limit and ask it to give you the feasible solution that has the largest, that has the most extreme value of the objective function within the time allotted. And there's a third possibility that, well, there are two other possibilities. The solver can determine that there is no feasible solution, or it can fail to find any feasible solution. The smarter the solver and the more algorithmic tricks that it has, the faster it's going to reach the global optimum. The better, the higher objective value solutions it will find within a given time allotted, and the more likely that it will find any feasible solution to begin with. So the value of Gurobi and Cplex and Express is that they are orders of magnitude faster and more likely to find solutions than the open source solvers. They are all using basically the same algorithms, but there are probably heuristic strategies that allow the commercial solvers to make a lot of progress very rapidly.
Like the API is essentially the same as this, right?
It's very, they're very similar. They all have very similar APIs. So we're still inputting the problem in canonical form. We're going to get to a point where we're inputting in symbolic form, and all of the major solvers have both interfaces. Okay, so what's really neat is that since fairly recently, SciPy has had a built-in mixed integer linear programming solver, and it is a wrapper for pies, and it has a really simple interface. It's not quite the interface as linprog, but it's close. So the first argument is the objective coefficient vector. This keyword argument, integrality, is an array of integers that tell it what type of value each variable can take. So this line says that we require all of the variables to be integers. And then we pass the constraints inside this linear constraint object, which takes a coefficient matrix, and it can take a lower bound and an upper bound. If we don't pass a lower bound, it defaults to just not having any lower bound. So this is it's saying the same thing as AX is less than or equal to B. So the exercise here is just run this.
Integrality, is that where you would feed something to tell that some quantities can be not integers?
Yep, exactly. If we look at the documentation here, integrality, we have several different options. 0 means continuous variable. 1 means it's an integer. 2 means semi-continuous, which means that it must either be within the bounds that we specify, or it can be 0. Semi-integer, similar, but must be integer. So yeah.
Like if I have coffee and donuts, and like if X is coffee and donuts, then I would feed it something like, and say I can take non-integer donuts, then I can do 1 and 0.
Yeah, exactly. Okay, so let's just run this. Sorry.
Hi.
Yep.
Yeah. Sorry. I was still confused about the first question, so I just wanted to ask this. When we define the C array, we have defined the programming, like the cost function is defined in terms of the lines of programming code that the students can write, right?
Yes.
Uh,
Per treat.
Wouldn't it make more sense to have the cost function for like the total budget there? I can understand why we like in the problem we don't have to minimize or maximize the amount of programming lines the students can write. We need to maximize the amount of uh, the cost for the snacks, and then from the optimum value of the snacks that we get by solving the problem, we can then calculate the required lines of code, like the final answer for lines of code. Wouldn't that make more sense?
The question is, can we minimize the cost? Can we make a constraint on the minimum number of codes, the number of lines of code written, and then minimize the cost to write that many lines of code? Is that right?
I like the question. When I read the question, it says each student how okay, we have to constrain both. That is what the question is. I see. So I was thinking in a different line, that whether if we just constrain the budget and then we calculate the lines of code, but then it wouldn't make sense to do a multi-linear problem. Yeah,
This is a pretty contrived problem, but it may be that if you express it the other way, that you minimize the number, you have a minimum number of lines of code that the whole class must write, and you want to minimize the number of dollars that you have to spend, you may get a similar type of solution. I don't know if you'll get exactly the same solution, but there probably are many, many equivalent ways to express this problem. There often are.
Yeah, okay, this answers my question. Thank you.
Okay, good. So, so once you run this, you'll get this answer. So, adding the constraint that the variables must be integers results in somewhat fewer lines of code, but not drastically less. Some gets
Change to muffins, although they are entirely equivalent in copy, aren't they?
So there are probably multiple. So this is giving us a feasible solution that achieves the global optimum value of the objective function. It is not necessarily the only such solution. There are modes of these solvers that we can call to enumerate optimal solutions when multiple such solutions exist.
But like, okay. I mean, it would be, yes, basically my question is, how do the solvers work intrinsically? I would have assumed there's some random walk-like thing such that people in this room get to slightly different optimal solutions with 5 muffins and 32 copies.
Mhm.
That does not seem to be the case.
So we'll have a chance to look at some more detailed out in the solver, which I think is going to partly answer that question. So hold on to that until the next exercise. In the back.
So basically, it's just picking a solution, and that's like it's only picking this because we've only like in the eyes of the linear program, we've weighted muffins and coffee the same. Because we wanted to incorporate how many trips to the bakery we have to make. You have to add another constraint to represent that.
Right. So there is a globe. It is found the global. It is found there. It has proven, the solver has proven that the maximum number of lines of code that we can write is 4,320. It has given us one such solution that achieves that optimum. There may be other solutions. But the solver at all times keeps track of both the best incumbent solution, the best solution that it's found so far, and also a bound on the highest possible value of the objective function. And it terminates when the objective value for the incumbent solution equals the bound. Which is the longer answer that I was going to give. Okay, so exercise 5. There is a sale on bagels. They are half price when you buy them by the dozen. How do you incorporate this into your model? Any ideas? So
But we multiply the inequality regarding the budget. We multiply the inequality regarding the budget. Maybe that's not straightforward because you have to use some modulo operation and that's not needed. But
yeah, we can only do linear equations.
Just make sure you're always buying dozens.
Yeah, but how would we do that? How would we do this?
By like making one bagel to be like a dozen bagels and changing the cost of one bagel to reflect the cost.
But see then we still need to buy an integer number of dozens. So we can still buy bagels singly. So go ahead.
So we can't, since the formalism is all linear, maybe there's some fancy math way to do it, but here we can't directly do modular arithmetic, but if we have a constraint where we're dividing the number of bagels by 12, we can enforce that has to be an integer as part of the constraint. Right?
That's one way to do it. There's a simpler way. In the flower plus.
Can we just add another, right, like another point to the vector, right?
Yeah.
we add some auxiliary variables. Would you like to show us how to do that? Thank you. Oh, go ahead. Okay.
What's the cost then, what's the cost of bagels again?
Oh, so remember, that's your objective right there.
Right.
So the bagels are half off if you, when you buy them by the dozen. So a single bagel is $2, a dozen bagels is $12.
Those bagels is $12, and then, sorry, what was the productivity for bagel? It was 100, right, for one?
Well, so let's look at our, yeah, no, this is fine. Okay, so here's a little quick reference. So X0 is tea, X1 is coffee, X2 is muffin, 3 is donut, it's fourth bagel. So bagel is the last element.
Yeah, okay. So, but it's not, right, it's not, is it 70 times 12?
No,
Or
because
one of those, yeah.
so we're not buying a dozen bagels and then giving a dozen bagels to a student. We're buying a certain number of bagels
I see.
and then we're distributing.
Okay.
So,
okay.
So what are the new variables that we want to have?
Well, okay, so I mean, I had been thinking like one bagel and then a dozen bagels, another variable, but I guess that doesn't. Thanks.
So how many new variables are we having?
Well, I was, again, just one for the, but. A dozen bagels. But,
Let's try it. So how do you, so you have, so this is the constraint on everybody gets at
Drink.
least one drink,
Right.
everyone gets at least one pastry, everybody gets a donut.
right,
This is the cost.
right.
So when you add, if you add the number of dozen bags of bagels as a variable, what additional constraints do you need to have?
Right. So, I mean, it has to be added to the cost, right?
So the cost is up there.
Sorry, it has to be added to, right, it can't be less than 180, right?
I'm sorry, I'm
Yeah,
confusing
yeah.
the cost function versus. the-
No, yeah,
the budget.
sorry, yeah,
No, you're right, it has to be added to the budget.
right,
So let me give you that.
yeah,
I
okay,
would add 2 new decision variables.
okay,
The number of bagels bought by the dozen, and the
Mhm.
number of additional bagels bought singly.
okay. So, but does that replace this bagel
Nope.
here, or?
Two
Okay.
new variables.
All right. Okay.
Isn't the second one just bagels that make you produce 79 code? Code? I mean, that is bagel code. Singular.
So you have. So what I'm saying is, there are 3 bagel related variables here. There is the number of bagels that we have.
Oh, total number of
The number of
bagels, yes.
bagels that we bought by the dozen, and the number of
Yes.
bagels that we bought singly. Go ahead.
I see.
Why can't we just introduce this as a new constraint? Like we could say, a new constraint could be, in the matrix, like one, for the bagel, so like bagel is the last one, so like 0, 0, 0, 0, 112 is less than some large number and enforce that to be an integer. So we get an integer number of bagels and then we can subtract that division from the cost.
So I
Why
think
does
that
not
to
work?
enforce,
Because we need an integer number of dozens.
yeah.
I
Yeah,
guess
so you have,
don't have that information in cost. There.
yeah, so you're saying, can we add? So we have. The number of things, because there's still a possibility that the optimum solution might involve buying. So many dozens of bagels and so many single bagels as well.
I think I understand. No.
Yeah.
Okay.
So, okay,
So-
so let's say. 0, 1, 2, 3, 4. X5 is the number of bagels bought by the dozen.
By the dozen, right?
And X6 is the number of bagels bought singly.
But then by the dozen, is that 12 times 70? Like, if 70 is the number of lines of code.
Let's try it.
Okay.
So you just
Okay.
make all the changes that you want, and let's discuss it.
Do we need to do additional values for the, because we can add a new item that is two bagel cost 2, and then we can have the it only in the C with another 70, because you every time for a bagel you need to write 70 lines. Doesn't change for the student, because the student doesn't want to pay.
Oh. Well. So I think you're right. I think you're right. And the reason, so if it wasn't for the constraint that every student gets a donut, then, so the constraint that every student gets a donut means that this constraint that every student gets a pastry is satisfied trivially. But if we were not to have that constraint and added, and we only added one new variable, which is the number of bagels bought by a dozen, we would not be able to write down the constraint that every student must get a piece of a bagel, or one student must get at least one piece. But the way that I wrote the problem here,
We need two more variables instead. We can just have like one variable which represents, like, we can take a box of bagel as one entity.
well, yeah, that's what she just said, and yes, that would work for this.
So we just need an extra constraint.
Yeah, but let's do it this way, because this is what my solutions look like. Okay, so we have 12 x5 plus x6 equals x4. I like it. So now we have,
And I changed this here so that it's this sum
Yep,
to represent
I like
the
it.
price.
and x4 went away from the cost function. I like it.
Bagels are half off, so the 12 should be a 6.
Nope, they're
No, no, 'cause
$12
they're
a piece.
$2,
Sorry,
yeah.
$2 a piece. So they'd normally be 24 to the dozen, but they're half price. Okay, so does anyone see, does everyone like this?
You have to change the matrix.
Well, we've got to change the
Right,
matrix but
I
before we do
missed it,
that.
yeah.
Yeah,
Inequality instead of.
yeah, that's right.
Right.
So, what should this, so this is true, but it's not something that we can put into the canonical form. So what should this be? Less than or equal to or greater than equal to?
Maybe less than equal to, because you're never gonna want more than if you're minimum.
So the number of bagels purchased must be, or the number of bagels by the dozen plus the number of bagels singly must be less than or equal to the total number of bagels. Is that right?
How many is both greater than plus than?
What's that?
You both, then it's equal.
No, but we can't do it in, that wouldn't fit in the canonical form.
Would be another constraint, right?
Yeah, I have another constraint where it's now.
Oh, yeah, you could. But, so you certainly could add both greater than or less than or equal to. But if you have just that, if you have just greater than or equal to, that is sufficient. The number of bagels that you purchased must be greater than or equal to the number of bagels that you have. That, you could add the less than or equal to, but it wouldn't change the solution. Go ahead.
I have
Yeah, go ahead.
also a
Yes.
question, but we know that the solution is 0 bagel. So when you go to buy the bagel.
Yeah.
And you select it's I see. Um,
Yeah.
This information is really useful.
Well, we're not getting into whether we like bagels more or donuts more. It's just that we want to write as many lines of code as possible. Yeah, so you'll see that the solution is different because I made sure that it was. Go ahead.
So, our X5 variable represents the whole unit of 12 variables.
Yes,
So I don't think we need the 12 multiple with X5.
so X4 is the total number of bagels that we have to distribute to students. And that must be less than or equal to the total number of bagels that we purchased. So X5 is the number of dozen boxes of bagels. Yeah, yeah, that's okay. Okay, so I want to make two corrections to the cost function, or to the objective function. We get 20 lines of code for tea, 100 for coffee, 100 for blah, 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 blah. So you get 70 per donut distributed, 840 per donut by the dozen, 70 per, I think we're double counting. Yeah, so these are 0. Okay. So I'm gonna, just in the interest of keeping us moving, I'm gonna make these modifications here. So we have two new variables, they don't affect these constraints at all. They do affect the cost. Okay, and then we have one new constraint that, so we want 0, 0, 0, 1, minus 12, minus 1 is less than or equal to 0. Okay.
See if that matches with my solution. Other than the fact that I made a typo. Yep, looks good. Okay, so let's put these numbers in. You can save yourself some time by copying these arrays because you only have to make a few small changes to them. Let's see.
Zero there.
You need to add a 0 before the 180 in B.
After, I think, because I added this as as a new constraint after the.
Oh, sorry, mine's at a different order.
Yeah, that's okay. Okay. It looks like we bought a dozen bagels. What part do people want to see? The solution here or the coefficients? raise your hand when you're ready to move on.
Or like code usage.
Yeah. How many people did you get?
I love 46 rate.
46, 40. Oh.
Yeah. Maybe I messed it up. I don't know.
How does your,
Oh no, wait, no, it's I think it's. Oh, I got this.
yeah. Well, how much longer do I have? Okay, right, we're going to, if I'm the last thing to do that.
Yeah.
Would this also work if instead of having 7 variables, you had 6, and your last and second to last ones were just bagel spot by the dozen to bagel singly, and to print out your answer, you keep that two together.
Yeah. So that, what I was saying before is that I think that we might have some trouble with correctly expressing the constraint that each student must get at least one pastry if we only added one auxiliary variable. But because the constraint on the number of donuts makes this constraint trivially satisfied, we could remove this. So that's why that would work. Go ahead.
So there's multiple ways to write the same set of
Yes.
constraints. What do the optimizers prefer, like performance wise?
Yeah, so that's one of the downsides of mixed integer programming. It's often something that is particular to each solver, and it is largely a matter of trial and error. And it's not always that the fewer variables, the better. Well, and it's not even that the fewer constraints, the better. But, so actually, this is an interesting example here where we're relating, X5, X6, and X4. The straightforward way of modeling this is to have equality here, but we made the model simpler by relaxing that to greater than or equal to, because it's a change that doesn't affect the solutions. This is so it's very common in mixed integer programs that you do what's it called? No, I think it's just called a relaxation. And some relaxations are approximations, and some are this is a relaxation that's not verified. Relaxations. Can I move on? Great. Okay. I know you're probably getting tired of this toy pastry problem and you want to do some astronomy, but we have one more exercise. So we've been playing around with the SciPy interface, which takes the canonical form as input. However, HiSpy also, so HiSpy, which is the first party API for this solver, also has a symbolic interface. So we're going to import HiSpy and we're going to make a model. And I've already constructed variables for you. So each of these Python, so we have a model object here. Every time we call model.addIntegral, that adds an integer variable to our model. So I've created all of these variables for you. And what's neat about this is that we can just write these constraints as inequalities in Python. You can see how with problems that are much more complicated than this would be a lot easier than figuring out all those indices and coefficients. So the exercise here is just to complete these constraints. So we have 20 t's plus, and actually let's just copy this again. Twenty t's plus 20, oh, plus 100 coffees plus 100 muffins plus 20 times bagels. No, 20 times donuts plus 70 times bagels. So there we have our cost function. Now we've got to add these other constraints. So we have a constraint that muffins plus donuts plus bagels is greater than or equal to 30. And a constraint that donuts is greater than or equal to 30. And a constraint that bagel or 12 times bagel dozens plus bagel singles is greater than or equal to bagels. And now we just run it. Oh, thank you. Model.add constraint. Let's see. Here's our budget. Oops.
Not having budget constraint should that basically lead to you buying infinite amount of everything instead of buying.
So see the error message here. It says primal, infeasible, or unbounded. So that's what it said. It's saying either it's not discriminating between. So infeasible would mean that no solutions exist. Unbounded means solutions exist, but the decision variables take on infinite values, and it doesn't distinguish between those differences. There we go. Same solution. All right. So take a couple minutes. It doesn't matter too much if you get the same answer here. I just want you to have some practice with entering these constraints symbolically. Because, and it doesn't matter too much if you get the same answer, because this is the last exercise related to the Muffin and Lemonade Lab. After this, we go on to some actual observation. Go ahead, Ethan.
I thought operators and take one of these variables.
No, because it only does linear optimization. Yeah. So if you want to have nonlinear operations, often you can exactly represent them by introducing auxiliary variables. And when that fails, there are a couple of other strategies. You can linearize the problem and solve the linear problem, and then, linearize around that solution, solve again, so on and so forth. Or you can have a lookup table or a piecewise linear representation of that function. We've got decision variables that say
which segment of that piecewise approximation you're on. Or you can discretize the entire problem, have a lookup table. Like let's say that your variable is, I don't know. I don't know, let's say that we need the logarithm of the number of copies. You could have just a table built into your model. If it's between this value and this value. Some of these solvers can also handle quadratic terms. But I don't have much experience with doing that. This applies. It will be does pretty well with quadratic terms. Okay, raise your hand when you're ready to continue. So you said we were going until 4 or 4:30? 4:30. Okay. Do people want to take a break? Let's take a break. 10 minutes? 5, 10 minutes? Be back here at let's round it up to, let's come back here at 4, come back in 10 minutes, be ready to start again at 3:55. Thanks, everyone.
Yeah. I don't know where.
No, so so bagels are those, dozen bagels is 12 bagels. Every time you buy a dozen bagels,
Well, and that's just, like, that's figure out what country. Yes.
Yeah, I mean, I've been trying to, I tried, that's why I tried like. South, east, west.
That will sometimes help you unless you apply to borders, but then you still have to get.
Yeah.
Then you're gonna get some of the redundant and that's that.
Which is what it sounds like. And I was hoping to be like, I would. Like help it out that.
Which when you do a lot of these, like I think all the stuff.
That's okay.
I haven't been with close enough, but I don't want to. And it may or may not be the finish my presentation. Right. It'll be okay. I'm really sure knows what I kind of. I think my tendency. Oh, no, those people see it. Yes. Again, we're not going to be like a different platform.
Oh. Yeah, I think because of that, our this, whatever the six items of goals. As they were, probably when the site was out there and you change it. And there are also things that allows pictures and. Sometimes it's just look at this. Like first thing comes to and one day is sometimes you know, for it will be like a good they're like, that's their position.
This one, I mean, this is two. Great. Right. Yeah. Just because like right? Yeah. Yes. It's kind of. Yeah. But it's like okay with the like. They get this. I could like spending a walk out, draw that, make what is again. Nice channel of your them. Yeah, they're not good for. Not good for. So like, yeah. So, yeah. I don't think anybody's actually sitting here so it's like if you want. It's $6.
Oh, the name is around it.
Then.
Like if I did this by myself, I would, because as long as you.
Okay, that's what I said.
Well, okay, so you could try to look at it. It might not be about linguistics, it just has a multi-section. Yes, because there are a lot of other people that work. This is interesting. There are a lot of. This is interesting. It's a three-letter word that comes after war and it's not war.
Just like. History though, here,
Okay, so.
It's a word, right? It's like a name of a word.
Click on the input and it'll tell us what we're going to need to click on, and that means it's going to say what you get. This is an offspring. I don't know.
It's probably has like some languages, right?
Yeah.
Or like in some language.
Yeah.
The name is, you're right.
Sometimes from the.
Yeah.
We're gonna try that.
It's better.
Also, I know where it's going to go. German and something.
Okay, so what update? Okay, I think we should guess like the language. Like that's gonna be.
Okay, folks, let's start back up.
Yes.
Okay, we can keep doing it.
So, yeah, we have half an hour and
We have yet to get to the fun part. Okay, so. Mixed interlinear programming allows us to solve optimization problems that involve decisions between alternatives or decisions that involve discrete quantities. A classic integer linear programming problem is the max weighted coverage problem, which is where you have a collection of sets, S1, S2, and so on and so forth, over elements, which I've just written as integers, 1, 2, so on and so forth. Each of these elements has a weight, W1, W2, so on and so forth. And we want to find a collection of a subset of all of those sets, such that we are taking no more than K of those sets, and we want to maximize the sum of the weights of the elements that are inside the union of all of the sets that we selected. So in this diagram here, the elements of the sets are represented by these black circles with numbers. Each of these elements has a weight associated with it. Each of the sets, S1, S2, so on and so forth, is represented by a colored shape. So S1 consists of the elements 1 and 2. S2 consists of the elements 4, 5, and 6. All the elements inside this magenta box, and so on and so forth. And so there is a straightforward interlinear programming formulation of this, which contains a typo, which is that we want to maximize this. So we have two sets of decision variables. We have the decision variables y sub I, which are binary variables, which are 0 or 1, 0 if the element is excluded from the union of all the sets that we select, 1 if it's included. And we want to maximize the sum of all of the y's times all of the weights. Then we have another decision variable x, and x sub j is 1 if we have selected set j, and 0 otherwise. So we have the constraints that the sum of all of the x must be less than or equal to the total number of sets that were permitted. And for each element of the set, the sum of all of the x's corresponding to all of the sets that contain that element must be greater than or equal to 1. Any questions? I think this will be one that's a little easier to see how it works when we do an example. Yeah. Okay. So another piece of important background is that gravitational wave localization maps are sent out in the format of HEALPIX maps. HEALPIX stands for hierarchical equal area isolatitude pixelization. All it means is that it is a way of dividing up the unit sphere into equal area pixels so that we can assign a number to each pixel. And that number is just the probability that the true location of the source is within that pixel. So we're going to stop here and go back to the notebook for just a moment. Because we're going to play around with HEALPIX for a moment. So what I've done for you is I have picked a gravitational wave event, and actually the name of the event and this GCN circular reference do not match what's actually in the code. So ignore these. I'll fix those for the final version that I'll upload. So I've done a few things for you already. I've written code to read the gravitational wave sky map, to convert HEALPIX coordinates to right ascension declination, to find the HEALPIX pixels within each ZTF footprint, and to determine when each ZTF field is observed. So those parts we're not going to have to do. But there's sample code here which you may find useful, and you're welcome to reuse. So first we have a whole bunch of imports. We're going to read this sky map. And so here we're using a function from the package ligo.skymap and called read sky map. And in addition to reading it, we plot it using matplotlib. And it looks like this. Okay. And we're also going to get the event, the time of the merger from the metadata in the sky map. Okay. Yeah, go ahead.
What's the question?
Yeah.
Does anybody else struggle with loading the read sky map function? Because it raises a narrow likelihood that somewhere in the reading in part it fails.
Is anyone else having a? So, do you have any active site? So you probably don't. If you're a LIGO collaboration, they're a single sign. Anyone else encounter any error when they run those imports? Okay. So Heinrich, I think the best bet might just be a lab result. That's fine. Yeah, I'll try to track it down after the talk then. Okay, so now we need a model of the footprint of the ZTF camera. If we point it in a standard direction. So if we point the camera at right ascension and declination of 0, this is the layout So I've written a little code for you to here for you to generate that. We're going to download the positions of the ZTF reference grid. Which gives you a table which has the field ID and the sky coordinates of the center. And we can plot that. And it looks like this. We're going to filter out. We're going to select only the fields that are observable at some point during the night. So I have some code that uses AstroPlan here to do that. So it's just checking, you know, when the sun rises, when the sun sets, when each field rises, when each field sets. We can plot which fields survive that. Okay, now we're here at the right place for the exercise. Okay, so now we're going to compute the heel pix representation of the footprint of the ZTF focal plane on the sky. So what this piece of code here does is it sets up a heel pix map projection, and it uses this function called heelpi.queryPolygon to look up the indices of the heel pix pixels that are within a polygon, and it does that for every single chip in the ZTF focal plane. And if we run this, this gives us a pixelated representation of the ZTF focal plane. So the exercise here is just to experiment with this value n side, which is the resolution of the localization, or the working resolution that we use for describing the footprints. And so it's got to be a power of 2. So if we set that to 64, it gets a lot chunkier. If we set it to like 2048, it's going to take a while to draw, but nope. This is just I've just been scrolling down. Yeah. So you just run all of the cells until you get to this section that says heel pix representation of ZTF focal plane footprint. Is it the same error that Heinrich was getting?
It says either operand 1 D type will not be guessed from D type, something to D type. Still.
Yeah, I would suggest if you have any problems, switch to the Colab. Yeah. Sorry, this is okay. Yeah, this is now that this is getting a little bit more complicated and having more dependencies, it's more likely to break. Okay, so the exercise here is just to find the value of n side that just barely resolves the chip gaps. So take a couple minutes, play around with that number, and raise your hand when you have an answer. I want the lowest resolution at which you can see that there is a gap between each of these 16 chips.
Yeah.
So it's on. We could see that, so, how we just make it by megabyte. One more than, I think, one. So,
So the code that I gave you. That's, that's. Why would we need that for 30 minutes? You know, it's actually not something that nice about this exercise. Anyone have an answer? Go ahead. 256, let's try it.
Yeah, I can definitely see all the chip gaps there. And see if, yeah, so at 128, can't see them. Okay, so any other observations about or comments or questions about heel picks? Okay. So go ahead and leave that set. If you've been playing with that value, set it back to 128, because this number is the larger this number is, the more accurate our solution will be, but the longer it'll take the solver to run. So let's keep it set to 128 and rerun that cell one last time. Then run the last cell in this section, which just in all this does is in a loop, it computes the heel picks footprint for every single field. All right, let's go back to the slides. So the way that we use this max weighted coverage problem is that each of the elements corresponds to a heel picks pixel, which is represented by these dots. The weights that correspond to those elements are the probabilities of the corresponding heel picks pixels. And the subsets that we can choose from are the footprints of the ZTF fields. So let's go and try that. Let's go back to the notebook. So I have started a notebook, highs model here, and I've made binary variables for each of the footprints, each of the fields, excuse me, and for each of the pixels. So now we need to fill in the rest of the model. Have at it. Maybe the objective function might be the easiest part. The constraints are a little tricky. So what should I try to maximize here? Yeah, go ahead. Not how many times. Remember that, so we want to maximize the total enclosed probability, which is the sum of so making the analogy to the maximum weighted coverage problem. That is the sum of all of the weights times all of the element variables. So one way to do this is a dot product. I can say numpy dot dot pixel vars comma prob. Okay. Now, if I just ran the solver right now, it would actually find a solution. And the solution is that it picks every pixel because I haven't given any constraints that tells it that can't. So there's another, trying to take care of the low-hanging fruit. How do we write the constraint that we can observe no more than 30 fields? Sum of the field variables is less than or equal to 30. Okay. Now the last constraint is the hardest. The last set of constraints is the hardest. So we know that we are going to need a for loop. So for, and then let's look at let's go back to our so for I in range len pixel vars, model.add constraint, and there's something that is going to have to be greater than or equal to the pixel variable. And so this something is the sum of all of the variables for the fields that contain that pixel. So we have this array footprints heel picks, which is a list of lists. Each element in this list is the list of pixels within a given field. So we need to invert that. So first we're going to make an array of empty arrays. And we need one for each pixel. And then we need to loop over them. So for j, i's for jji or for j pixels in enumerate footprints field picks, footprints field picks inverse. Oh, yeah. For I in pixels, footprints field picks inverse I dot append j. So that'll take our lookup table, our table that converts fields to lists of pixels, to a table that converts pixels to lists of fields. And now we can do sum of field vars j, or j in footprints field picks inverse I. And that should do it. See what we get. Okay, it found an optimum. So we can ask it what objective value did it find. Found a value of 0.39 something. So there's a 39% chance that the true position of the gravitational wave source is in at least one of the fields that we selected. So then we can get the value of the flag of the variables for these fields. And then we can use that to look up the information about the fields that we selected. So these are the 30 fields that we picked. That I went really fast there, and I see some heads shaking. Have I lost everyone completely? No? Go ahead, Ethan.
Straight, like number of fields of
There is no such constraint. The field, multiple fields may overlap and multiple fields do overlap. But if we select two overlapping fields, then the pixels in the overlap region still count on the links. That's what makes this a maximum weighted coverage problem. Yeah, right.
Sorry, what was the constraint you added inside the board? Can you go back to the?
Yeah. So this constraint, or this set of constraints, says that so all of these variables are flags. The field vars is an array of flags that is one if we choose to observe the corresponding field, 0 other ones. Pixel vars is an array of flags that corresponds to each of the pixels, and it's 1 if the pixel is inside any of the fields that we've selected, and 0 other ones. And so what this is saying is that take, so for each pixel, sum over all of the fields that contain that pixel. That sum, if any of those fields is selected, then the pixel must be selected as well. So for example, let's say that I have field 1 and field 2. And I have pixel 1, pixel 2, and pixel 3. And let's say these are the only fields that I have, these are the only pixels that I have. Then what these constraints would say is that, so remember the X's are the field flags, and the Y's are the pixel flags. So X1 is greater than or equal to Y1. What this means is that if field 1 is selected, then pixel 1 is as well. And then I have the constraint that X1 plus X2 is greater than or equal to Y2, because both field 1 and field 2 contain pixel 2. So if either X1 or X2 is non-zero,
then y2 must be non-zero as well. And then similarly for x3 is greater than equal to y3. This is an inclusive OR. That's so this means, so if I have A plus B plus C is greater than or equal to D, this means if A or B or C, then D. Okay. Questions? All right. So we ran the solver. And now we can just plot the fields that we selected. So this looks funny up here because it's not taking care of fields that cross the edge of the map. But if you look at this and compare it to the sky map, they look kind of similar. We've put fields where there's high probability, which is good. Okay. So now this is now this gets a little bit more challenging. So we've picked the fields that we want to observe. Now, don't be scared. We don't need all of these equations. This is a translation dictionary that goes from logical statements on the left to mixed integer programming representations on the right. Yes, Ethan?
All right, I'm going back to this is just saying that, like, if you pick a field, you better also pick the pixels.
Yes.
Right?
Yeah, that's right.
But you're probably searching over these things constantly. You gotta make sure that, like, your solution is logically consistent.
So what this is doing is saying we are optimizing over we fundamentally want to pick the set of fields to observe. We have a set of auxiliary variables that represent the pixels that are within the fields. And we need, so the constraints that we just added made it so that if we select any of the fields that contain a pixel, then we must select that pixel. We don't need to, it's really, there's a converse that if we select a pixel, then we must select at least one of the fields that contain it. However, we have taken advantage of a relaxation by not writing both sides of that converse relationship, because we don't need to. It doesn't change the problem if we make that relaxation. Okay. So, all right. So the real power of integer linear programming is that you can represent pretty much any logical statement as a series of linear inequalities. So for example, if you have a binary decision variable a binary decision variable A, and you want to have a variable that is not A, it's just 1 minus A. If you want to say that if A is true, then B must also be true. That is, B is greater or equal to A. This is a really useful one. If A, then f of x is less than or equal to 0. So f of x is some linear combination of decision variables. So here's how you do this. You introduce a constant m, which must be sufficiently large, and essentially m must be larger than any possible value of f of x. So then what this does, let's say that A is 0. So then this whole quantity is 1. So this right-hand side is a large constant, m. And that constant must be greater than or equal to f of x. And that constant, we already said, is larger than any possible value that f of x can take. So this constraint is trivially satisfied in that case. And so that turns off this constraint if a is 0. Now, on the other hand, if a is 1, then 1 minus 1 is 0. So this entire right-hand side is 0, and we're left with f of x is less than or equal to 0, which is what we wanted. So this is a way to have a decision variable turn another constraint on or off. Okay. So
The last exercise here is that we want to pick what order to observe these 30 fields in to maximize the number of fields that we can observe. Now, these fields, I have picked an exposure time which is long enough that we cannot observe all 30 fields in a single run. So what we're going to do is we're going to, so that the scheduling is going to be a new optimization problem. I've introduced two decision variables, a binary vector, which has one element for each field. It is 1 if we decide to observe that field, otherwise it's 0. And then I have introduced a vector of real value decision variables, 1 for each field, which is the time that we start the observation if we choose to observe that field. And these variables must be bounded by the earliest and latest possible observation times for those fields. And we want to maximize the total number of fields that we can observe. And we have these decision variables that say whether we observe each field or not. And so the objective function is just the sum over the x's. So now we can only observe a single field at a time. And so that means that no two observations can overlap in time. So in pseudocode, that is, if x sub I is 1, if we decide to observe that field, then either the start time of the observation plus the exposure time delta must be, or the start time of observation I plus the exposure time must be less than or equal to the start time of observation j, or the start time of observation j plus delta must be less than or equal to ti for all j not equal to I. So what this is saying is you have this timeline. And for each field, we have the time that the field rises and the time that it sets. And these might be different for all of them. Okay. And then we have the time that we actually choose to observe each field. So let's say that we start observation 1 here and we end it here. Then we start observation 3 here. Or so we start observation of field 3 here and end it here. And then we start observing field 2 here and we end it here. So what this is, so we have, this is T1, this is T1 plus delta,
This is T2. This is, or sorry, no. This is T2. This is T2 plus delta. This is T3, and this is T3 plus delta. And we don't want any of these intervals to intersect. Okay, so this last exercise, and this is a relatively challenging one, is to take this logical statement, transform it into a system of linear inequalities, and then write it as a mixed integer linear program. And I've started that program here. I've given you decision variables for your observation times and whether you select a given field at all. And I've also added an auxiliary variable, which you'll find out that you need. But so let's go back to this. Actually, I'm going to post the solutions now that we've come to the end, or I will, shortly after we close. We could either, we can do one of three things. We can simply have no. We can struggle through this together using our dictionary here, or I can show you the solution and I can explain it. So raise your hand if you just want to hear now. Okay, I'm not offended. Raise your hand if you want to struggle through it together as a class. It is. Like raise your hand if you want me to show you the solution and discuss it. 2, 3, 4. What's that?
We're a little bit past. Yeah, we should probably.
Okay, so what do you want? So you're the boss. What do you want me to do? Stop you.
I think the last one. Sure, kind of show people.
Okay, show it and discuss briefly. Okay, so this is let's see. Oh, that's interesting. I think I wrote the constraints, but I didn't write the solution as math. So, okay, so the logical version is if xi, then ti plus delta is less than or equal to tj, or tj plus delta is less than or equal to ti. Okay, so first thing we can do is so this if then we can get rid of by saying ti plus delta x sub I is less than or equal to tj, or t sub j plus delta xj is less than or equal to ti. So if we choose not to observe a field at all, then there's no reason that the start times of these two fields can't be the same. We'll throw that if we don't observe a field, then we just don't care what value of the observation time for that field. Okay, that's step one. Step two is that we introduce an auxiliary decision variable or matrix of decision variables, S sub ij, which is defined as one. Sorry, it's too much. One, if we observe field I before field J, and 0 if we observe field J before field I. So it just determines the order that we observe things. Okay, so then we go back to this dictionary and we use this one. If A, then f of x is left equal to C. So we have two cases. We have if A, so so let's handle the case that we observe field I before field J. So that is this inequality here. So that becomes Ti plus Tj, or no, sorry, Ti plus delta x sub I minus T sub j is less than or equal to m times the quantity 1 minus a. Okay, I just used this substitution. And then we have the other case that S sub ij is, or sorry, it shouldn't be a, that should be S sub ij. And then we have the case that S sub ij is 0. We use the rule for not, which is that we do 1 minus a. And so now it's this side. Copy that down here. T sub j plus delta x sub j minus ti is less than or equal to m. And 1 minus the quantity 1 minus s sub ij is just s sub ij. So then we've converted our sort of logical pseudocode into a system of inequalities. And this makes the problem actually much more computationally challenging. Oh, by the way, I forgot to discuss what the value of m should be here. So m needs to be larger than any possible quantity that the left-hand side of either of these equations contain. So remember that this left-hand side is the end time of one observation minus the start time of another. So how would we go about finding a suitable value for that? Go ahead. Yeah, that's right. Could be how long the sun is down, for example. Yeah. Okay, so one other small issue here, because this makes the problem take a lot longer to solve. I added this line here, which sets the maximum solution time to 60 seconds. So it's not necessarily going to find the optimum, but it will find the best possible feasible solution in the time, and it will tell us how far from optimal it could be, or a bound on how far from optimal it could be. Okay, so I'm sorry I'm over time. Thank you very much. I'll ask me questions offline if you have any. Thank you.
Thanks, everyone. Night. Yeah.